know just about all of you, but I'm Clay Hiles, the Executive Director of the Hudson River Foundation. Sarah, are we live to the world?
Yes.
Live to the world. So welcome all of you in the room and the great webinar in the sky. The Hudson River Foundation, which is hard to imagine that, about to have its 40th birthday in a couple of years, was born of a settlement. Virtually all of you know of this, famous Storm King controversy. And in the settlement agreement, there was an attachment that listed various things that were going to be part of it. And the Hudson River Foundation appeared in just a few paragraphs. Obviously, later there was a lot of lawyers made a good living putting together the charter and bylaws and the ROE today. But in that original paragraph, it said that the foundation was to be established to support research on the Hudson River. We later made clear that that includes not only the river, the estuary, but the watershed, and to disseminate the results of such research. So this is one of our acts of dissemination. We've been doing that for nearly 40 years, and in many ways that John Sikowski can describe in detail. He's the keeper of the stats, but more than 40 million, of the original $12 million, more than 40 million has been spent on scientific public policy research, and somehow we still have more than 40 million to spend. So at least we did it until a couple of days ago, I think maybe a little less than that. But we have tried to live up to the mandate for publishing the results of what was done in many, many different ways, from libraries full, and you can say by Orton, or the pushed away somewhere where not accessible, but libraries that were full of academic reports on the research in this room has done, to curriculum for the Hudson River Slip Clearwater, to a series of special reports we've done from time to time, because we think that it's important not to do anything as vulgar, which nice boys and girls and scientists don't do, as applied research, but we try, because we think this is our mission, to make our work and the research we support useful in the protection, restoration, understanding, and celebration of the Hudson River. Many of you, I think, probably waded through our reports on PCBs, including the one we produced most recently on the first understandings of what the results of the dredging have done. So on our website, we can get to it. Today, we have a particularly important instance of that kind of work. Dennis will describe how we got into it and what the particular people who are here to talk to you today have done. But of all the things I think we do, the one that's most fun, because it involves our social network, is just Ames Seminars, which began as Tuesday seminars, because we had them on Tuesdays almost never. This is a funny version of a Tuesday seminar. But several years ago, after many, many years of extraordinary leadership at the foundation, Edward A. Ames, or as we call him Ed, left the board of directors as an active member, and many years as chair, and turned the gavel over to the extremely worthy Bob Elliott. Both Ned and Bob, I am glad to say, are here today. And when we decided to name these lectures the Edward A. Ames lectures, it was because Ned, along with Bob, have been the most, I think, active of all our constituents in coming to these events, and I appreciate it. So Ned, raise your hand so you can. That's the very Ned Ames of the Ames Seminar. So Dennis, bring these people swiftly to the beginning of our seminar.
Sure, thanks, and thanks for everybody to be here. Let me take loud. Okay, I'll be loud. We've got two separate venues going on here. We have a number of people here, which we have, I guess, about 65 or 70 people sitting at our office. And for those of you that are on the webinar, which I don't know what we're up to, Sarah, but probably 80 or so folks, this comment's directed to you folks that if we're going to go through the presentations of Phil Orton and Dave Ralston, and we just ask you to hold your questions till they're finished. Those of you on the webinar, you can hopefully see us and hear us. You can't talk directly to us other than writing out questions. So whatever questions you may have, if you write them and click on the little chat box on your screen, there's a little balloon. You can write out a question, and we will take those and we will answer, or Dave and Phil will answer questions until they're completely exhausted. What I wanted to do was to provide a little bit of background before we get into the presentations as to, what is the Hudson River Foundation doing, and, what did it do to try to attract all these people that are here today? Well, it turns out that we're here to talk about barriers, and barriers are something that is not necessarily a new concept. It's barriers for a variety of purposes have been discussed kind of in engineering and academic circles, and we have one or more people that have been talking about barriers for quite some time to either mitigate storm surge damage or improve water quality and so forth. But these concepts have been around for quite some time. But notably have piqued probably your interest, or most of the interest in this room and on the webinar, is that these large barriers are part of a strategy that may be considered by the Corps of Engineers in their harbors and tributary study, better known as HATS. Our interest is that, given, and probably your interest, that as one begins to think about reducing the flow into an estuary, like the New York, New Jersey Harbor Estuary, the Hudson River Estuary, there's a potential for large-scale ecological change. And given there's potential for a system-wide change, we indeed thought that there's a need to have some discussion of that particular issue. And in particular, if one wants to get a handle on what the ecological impacts might be of these kinds of structures, one has to think that there's got to be relevant science needs to be brought to the table, both science that have been done in the past and that will be done into the future. So again, why us? Why are we involved? Well, we sort of have two missions here. One is, as sort of Clay articulated, we're a funding agency for scientific research, and we've funded research for over 35 years here in New York Harbor and the Hudson River. And there's a large body of information that does exist. A lot of the work that we fund is, again, targeted towards public policy issues, and that a lot of the work that we fund, sometimes we don't even know what the issue may be, but in subsequent years or decades, it may appear to be very important. In the case of some of the work that we've done in the past, I think that, for instance, work on the way that larvae move in and out of the harbor was going to be extremely important in an eventual evaluation of barriers. We also have a relatively new function here at the Hudson River Foundation. It's been 4 or 5 years, but it's us hosting the New York, New Jersey Harbor Estuary program, which has a convening function of bringing together federal, state, local agencies and nonprofits and individuals that care about this estuary. And this issue has come before the policy committee of the Harbor Estuary program, and they have encouraged Rob Perani and the program to be as involved as possible in producing either science, convening information, having discussions. So it brings us back to, if we're going to take a look at what the impacts might be of these structures, we have to start somewhere, and that was a kind of a difficult discussion that we had for several months as to what needs to be done. But we came to the understanding that if we want to know what's going to happen eventually to fish, to chemistry, to the biology of the system, it starts with the physics. And that as we look at what the constraints on flows in and out of the harbor might be, whether it's circulation, whether it's stratification, turbulence, a variety of things, we sort of need to know the physics first before we start moving on to the ecological impacts. So that brought us to of the idea that we should be at least taking a preliminary look to look at what the range of impacts might be by a large barrier strung across New York Harbor. And to help us with that, we went to two folks that we have tremendous confidence with in working with them over the years, and their abilities and their experience just really popped out at us, and that's Dr. Philip Orton of Stevens Institute of Technology and Dr. David Ralston of the Woods Hole Oceanographic Institution. And we asked them whether they could put together some background information on barriers in other systems, and to do some modeling using some existing models to see how well they might do in providing us information so we can conceptually understand what the important questions might be on the physical side. And they've done that. And they've done that amazingly with few resources and little amount of time. It's unbelievable. I think that there's a lesson there. That if you have a really big
it's
topic,
a terrible precedent to set.
find some really smart people, pay them very little, tell them they have to be meeting by tomorrow, and you really are amazed at what you can get out of it. So that, and so I had a chance to look at their final report that's on our website that we're going to talk about today. I think you'll find it very, very interesting, and I think you'll find the talk today interesting. When they came up with a sort of a draft plan or draft report, we did have a webinar this summer with some of the people that are involved in the HAT study and some experts that are struggling with this issue elsewhere, such as Boston Harbor, and they provided some comments and so forth. They're now folded into the report that Dave and Phil will present to you today. What I just want, one last statement I want to make is that again, we are here not to be part of a strategy that's evaluating barriers for their efficacy in protecting property and lives. We're here to look at, should barriers be proposed, should they be looked at or even constructed sometime in the future? What does that mean for the sort of the estuary, the Hudson River estuary? So we're not the Corps of Engineers. We're not a state agency. We do have value added on the science side, and we're going to continue to do that, as sort of Clay mentioned. So anyway, that's a long-winded way of introducing Drs. Orton and Ralston. And go with, where's Phil? There's Phil. Start with
I think that's that.
oh, okay, I got it wrong already.
Thank you, Dennis. Did I break it? Yeah, thanks. This is collaborative. Phil and I both sort of took the tools that we had, tried to take a similar approach to the question, and then these tools in numerical models, each one has its quirks and differences, and does something better than others. And so we can sort of evaluate how each of them responds and say, well, how does that really affect how well we know this answer? I'm showing one example here of potential barrier taken from Wikipedia, but it's also pretty consistent with one of the alternatives being considered by this. Right, so we basically took out some existing tools, these models we have, and put a barrier in. We had to start, so we put a barrier roughly consistent with this, which again is consistent with one of the alternatives being considered by the Corps of Engineers, this one here. So it's basically a barrier between Sandy Hook and Rockaway, and there's different configurations as far as how you leave openings for navigation and for water to flow through during periods when you don't want to stop a storm surge. So most of the times these gates are going to be open. And so that's the condition we're modeling. We're not looking at sort of what happens during the storm surge conditions. Instead, we're just thinking about during normal operations, when you have normal tidal flow, what happens to, how does the system change as a result of putting places where you have fixed barriers in place, where there's not gates. For this scenario here, we have sort of a barrier across the mouth of Lower Harbor, but then also one in the East River. We focus mostly on this one because that's where a lot of the tidal flows happening again, just sort of keep things simple. This is by no means the only alternative being considered by the Corps. There's many alternatives, including barriers further up near Verrazano and through some of the kills. But again, preliminary, future studies can certainly dig into more detail as far as how different configurations might affect conditions in the estuary. Okay, so I've worked on the Hudson for a while now, and I know a little bit about how the Hudson works and how estuaries work in general. I've done zero work on barriers before, and so my first step was to educate myself on what are the influences of barriers? What do we see in other parts of the world as far as how barriers affect conditions in estuaries? And there certainly are barriers in other parts of the world. There's roughly a dozen or so, maybe a couple dozen relatively large-scale barriers around the world. And so we begin to sort of look at how conditions have changed as a result of putting those in. And some examples include in the Netherlands, in the Eastern Scheldt, the barrier to protect London on the Thames, and there's smaller scale barriers on the East Coast, and for example in Providence, and then a more recently installed one, which is sort of a similar scale to what we're talking about with the Hudson, is in St. Petersburg, Russia. The problem is, most of these systems aren't really like the Hudson as far as how they behave from a dynamics or estuarine physics point of view. And so we're limited in what we can learn from that. We're going to go into that a little bit, but the key differences are these are all relatively either broad, shallow regions with big tides, so lots of mixing, like the example from the Netherlands, and then also similarly one from New Orleans. Or they're pretty far off a river where you're just blocking fresh water, there's no salt involved. For example, several of them in Europe. Or fairly small systems where there's not much fresh water coming in, small river, and so this estuarine, the essence of an estuary is where the river meets the ocean, and all the processes that happen with the mixing of those two water masses. And so many of these smaller systems don't have a lot of freshwater input, so therefore it's a different set of physics going on. And then finally, this most recent one is in the Baltic Sea, where there's essentially no tides. And so that's a key component of sort of how the Hudson, and particularly many estuaries, vary on a daily time period, but then also at longer time scales. So as a result, a lot of these essentially don't have a lot of the salinity variation, which we see in the Hudson, and which is critical to both the dynamics, but then also to many of the ecosystem functions which we care about. But we're still going to figure out what we can learn from the systems that have been built. And so stepping back a little bit, start thinking about what do I mean when I talk about a different kind of estuary. So these systems, they're well mixed in the sense there's not a lot of stratification, there's not a lot of difference in salinity between the surface and the bottom water. And that's because they're relatively shallow, and then they have relatively big tides, or both. So lots of mixing energy, mixes up the water column, makes the system relatively unstratified. There's always a little bit of stratification hanging around, but we call them mostly well mixed. And so thinking conceptually about what we have here is we have I can't point at this thing. We have the tides on one end at the ocean, salty water, and we have the river at the other end, some sort of river input. And then we have a gradient in salinity. These are sort of lines of constant salinity. And again, there's not much vertical structure to that. There is horizontal structure to that, reflecting that gradient between the ocean and somewhere where it's fresh. And the key sort of physical process here in this type of system is that the tides are the dominant means of exchanging material between the ocean and the river. The tides are big, they're sloshing back and forth, and that's the main way you exchange material between material being salt, but then anything else you care about as far as biology, nutrients, and so forth. Yeah, and so that's, again, the tides are the dominant means of sort of transport, which is going to be in contrast to what we'll see later. Thinking about one of these Dutch estuaries where we have a relatively well-mixed conditions. The Dutch have been dealing with water problems for centuries, and so they also are very thoughtful, and they study a lot, and they put a lot of academic effort into sort of understanding what happens when they do these modifications to the coastline. And so this is, for example, this barrier in the Eastern Scheldt, which put in the late 70s and early 80s. And they did studies before and afterwards of the conditions in the estuary. And there's a whole body of literature on that. And so, for example, one of the changes they observed was that once you put this barrier in, this is kind of common sense when you think about it, if you block off a lot of the flow, some fraction of the flow, then the tides inside the barrier are going to decrease. The tidal amplitude is less. Essentially, you've taken energy out by trying to shove all this water through a barrier. or through an opening in a barrier. And so as a result, with weaker tides was doing the mixing of the salt to keep things from being stratified. So we can compare the conditions. In the black, we have the stratification, so the top to bottom difference in salinity throughout a year. In the black, we have the conditions before they put the barrier in, so very weak stratification. Again, this is a 1/10 of a PSU. This is practically nothing, but it is something. Whereas after you put the barrier in, that increases substantially. Weaker tides, more stratification. And why is that important? Well, it's important just from a physics point of view, but also from a biology point of view. With weaker tides, with more stratification, you also had, well, let's get to that. So weaker tides also meant there's less sediment getting stirred up in the water column. And so the combination between less sediment in the water column, which makes the light clearer, essentially, the water column more optically clear, so light can penetrate farther. Then they saw a marked change in the phytoplankton assemblage, essentially because it's stratified, phytoplankton can stay near the surface, they have clear water, and they can grow. And so they saw this change in the phytoplankton community in the system after this barrier put in. They also saw changes in marsh conditions and so forth because the tide has a weaker amplitude. So that's just one example. Again, so this is a factor of 10 at least less in stratification than we see in the Hudson on a regular basis. Another example, which sort of looking to Dennis mentioned briefly, or cited as far as another a regional example, which has been studied quite well. I mean, Boston is considering barrier alternatives. And so they put together a pretty comprehensive study examining basically how such potential barriers would influence hydrodynamic and other transport issues inside the harbor. And again, it's pretty big system, similar in size to the scale we're talking about, 4 miles or so. It's about 6 miles across, I think, for the lower harbor here. Yes. Okay. So the Boston study was really, well, I'll wait for that.
Can I ask a question?
Sure, yeah.
That example you just said, do you know what percentage of the channel is blocked off?
You know, for that study, I don't. I'll try to point that out for other ones, but for that one, I don't. It's a pretty big system. It's a really broad and shallow region. So for that's only be discoverable, but I don't know what that is.
Hey, Dutch Consulate in the house back here.
Hey.
I'm happy to get information for you on that side.
I didn't know you were back there when I was saying all the good big stuff like that.
Between the big ones and the small ones, there's more than 20 different barriers.
Yeah, that's right. This is part of a system of barriers, the Delta List. Yeah. Okay. Hi. No problem. It's coming out of your time, no problem. So the Boston Harbor study was a much bigger and much better funded study than we had. But as a result, they're able to do a much more sort of extensive and purposeful modeling of the proposed barrier systems. And so they constructed a model essentially which is designed to address that question, which is pretty key. Anytime you build a model, you're doing it to address the question. In this case, we sort of adapting models that were designed to do other questions and work pretty well. But in the Boston Harbor case, they really targeted their resources to resolving some of the processes which are important for flows of these barriers. And so one of the results they found was that at least within Boston Harbor, there was very little effect on the tide with some of the primary proposed configurations. I think this is it right here.
That was it.
Yeah. Yep. Okay, do I get to do it now? Okay, great. Yeah, so this is one configuration again, so a couple openings. And so one of the, I mentioned that, there we go. There's little effect on the tide, and the reason they hypothesized for that, and the reason they, the way they explained that was, Boston Harbor already has a natural set of pretty complex bathymetry, a lot of channels there. There's a lot of blockage there already, so adding these gates didn't have a big effect on the tidal propagation into the system. These are also big gates in the sense that I think they said this would have been the biggest gate in the world if it were built. They did, however, note that as a result of putting these gates in and funneling these flows through these gates, you do see big changes in the tidal currents. And so the tidal velocities, the speeds, increase substantially from sort of a knot or so in the natural openings to 5 to 6 knots. And that becomes an issue for navigation. It also becomes an issue because you get these regions where you have very intense velocities, but you also have these regions which are sort of dead zones where you blocked off the tidal flow, and therefore there's potential for reduction in exchange with these regions. And so that's sort of knock-on effects of that they sort of speculated about, but didn't address directly. Okay, so those are both sort of well-mixed systems, relatively well-mixed systems. Now I think about the Hudson. And the Hudson is what is the classic partially mixed estuary. This is, it sounds like a small difference, but it's a big difference. And the big difference is that, and I've tried to sort of draw it schematically, is that if you recall from the previous schematic, we've now gotten deeper, the tides are a little bit weaker, and the river flow is a little bit bigger. And those are sort of the key external forcing factors that control how an estuary behaves. And so, and you can think about sort of moving through different parts of parameter space. In the partially mixed system, we have sort of a balance of all three of these being important. And as a result, so now we have this salty water on one end, fresh water on the other end. And so that creates a density gradient. That creates essentially this water is heavier than this water, which means it wants to slide underneath. The river water is fresher and lighter. It wants to go out of the surface. And so that's happening all the time. This is called the estuarine circulation. And it's always going on with the tides sloshing back at about a meter per second. But we have this exchange flow, which is always bringing saltier water in at the bottom and taking fresher water out of the surface. And that's something like 10 centimeters per second. Again, doesn't seem like much, but you have to do that consistently through time to use import. And this is the main mechanism by which salt is exchanged with the coastal ocean. It's also the main way in which you get other exchange material of nutrients and so forth. And so in a shallower system, tidal mixing just mixes this out. You can't have this sort of two-layer circulation. But in a deeper system like the Hudson or weaker tides, then this two-layer circulation becomes really dominant. And again, that's just on sort of tides as a schematic here, but anyone who's been on the water knows that we have different sizes of tides depending on the phase of the moon. And so during neap tides, the tides are smaller and weaker, which means there's less vertical mixing, which means the estuarine circulation can get bigger, can get stronger. It also means the stratification can get stronger. Less mixing, bringing more salt to the bottom end, taking more fresh water at the surface, more stratification. During spring tides, mixing picks up, this exchange shuts down, and you have less exchange and less stratification. And that's happening every 2 weeks. The other factor is river discharge is changing. I'll say for the, again, preliminary studies, we picked a single discharge, which is about the average for the year for the Hudson. But one could certainly think about how that also is a factor in how the system responds. Okay, so this is a schematic. Let's look like in the real-ish world, a model version of the real world. So what I'm plotting here is a time series for a particular time when we were out there doing some observations. As we know, this was actually a pretty good representation of the system. We have the Hudson River. This is the model now where we're sort of simulating all the flows and transport of salt in the estuary, the tides, the salt, and so forth. And so we're measuring distance along the Hudson from right here at 0 kilometers on up the main stem of the estuary. And so that's shown on the y-axis here. And then the x-axis is time. So it's a few months in the fall, sort of moderate discharge conditions, similar to what we're sort of simulating. In a sense, but it's a realistic conditions. We're changing discharge with storm events and so forth. And so the top panel, I'm showing blue line with the river discharges, and then the black line is the tides. So you see there's a spring neap variability, which is changing every 2 weeks. There's also a lot of other stuff, which is essentially water sloshing around in the coastal ocean, coming up into the New York Bight and going back out. and that's storms and stuff like that. So it's a much messier signal, but what we do see is this response to the system. And so during neap tides, this is showing bottom salinity, so salinity at the bottom of the estuary, at the bottom of the river. During neap tides, the estuarine circulation picks up, salt comes in, and it goes all the way up to 80 kilometers or even farther. During spring tides, just a week later, mixing picks up, there's less import by this estuarine circulation. The river can push the salt out more effectively because there's less import by this estuarine circulation, and you get the entire system collapsing down to 40 or 50 kilometers. And so this fluctuation is happening every 2 weeks, and that's going to become important. For when we think about how, so this is what the natural modulation of the tides, and so then if we add any barrier-induced modulation of the tides, that will also have an effect on this response of the system. Okay, so one of the things I want to do is say, okay, are there any studies of of barriers in these partially mixed type systems? We found 2, and actually only 1.5. There's one, the first one I found was a really nice observational study, and what they studied was the effect of the removal of a barrier. So this is up in Sheepscot River, up in Maine, coastal Maine, and so what they found is they had a causeway there with a narrow constriction, and so I went to the charts to find out how narrow that was, and so this is about 350 feet across, and the horizontal clearance on the charts anyway is 30 feet. And so again, so a pretty strong constriction, but we also know that tides are very strong there, such that they put a warning on the chart. So essentially you have this causeway with an opening in it, constriction, restricting the flow through and increasing the tidal velocities there. So what they did is they put out instruments, they measured how the system looked before and after you had that, so the opposite of installing a barrier. So what they found was that once you remove the barrier, the tidal amplitude increased by 50%. There's less choking of the flow through the system. They also found that the stratification decreased. Again, so when the barrier is there, there's weak tides, weak mixing, and also more exchange flow. And so the same idea that changing the tides, so it changes the exchange flow and also changes the stratification. And those two things are coupled. And this is consistent with sort of that conceptual model. The other study that we found was a modeling study. And this was done thinking about some proposed or potential barriers in the Chesapeake, which is a couple estuaries south of here. But it's a well-studied estuary. And so what they did, they took a similar type of approach to what we did, where they took an existing model, which they think is good, and they installed barriers. And there's they did a couple different configurations. One is sort of with this really big opening region in the middle, and then one has this additional barrier here, since the 2 openings are much smaller. And this is, again, sort of just based on their reported areas. It's a 40% open area and then a 15% open area. And we'll talk more about what the numbers we tested in the Hudson with the models here. Okay, so what did this say about how this is also a partially mixed estuary, slightly different, but similar enough, more similar than the Dutch examples I showed before. So this is, again, so thinking about the Chesapeake or the Atlantic Ocean on up to Susquehanna. And so what they found was that for, ignore the green line, but for just the case with the relatively open barrier and for the case with the more constricted barrier, is the blue and the red respectively, they saw the tidal amplitude decreased. And so this is the black is the tide with no barriers at all. Blue is if you install the open barrier, and then red is if you install the more restricted barrier. And so the tidal reduction is something like 10 to 20%. Another thing to note here is these tides are relatively weak compared to the tides we have in the Hudson. And so that's another factor that we'll come back to sort of thinking about context for how we interpret these results with respect to the Hudson. They found that that's just showing the tide along the estuary. There's a lot of spatial structure, which is very interesting, and depending on where you live, you might be affected differently, or depending on if you're a fish or a person. And so what they found is overall, this is the change in tidal amplitude for those 2 cases. Blue means the tide is smaller. So inside the barriers, the tide is decreased, again, consistent with physics. And then right outside the barrier, there's the amplification. The tide is reflected by the barriers. They also found that the salinity intrusion increased, and also the stratification increased. And when you think about this, they took in a long channel section here of the salinity intrusion at different isohalines, so different lines of constant salinity. And so you can just compare with the black to the red would be sort of the no barrier case to the more restrictive barrier case. And you can see the salt goes farther in. It's also more stratified when there's the barrier there. Again, there's spatial structure to that as well. This is the change in stratification, where red is an increase in stratification. They're showing, several PSU increases in stratification through much of the region. There are, however, regions down in the mouth where you have the increased velocities right near the barrier where there is more mixing and there is less stratification. And so it's a combination of both those. So it's the fact that you have more mixing near here, but you have less mixing on up in the estuary because the tides are weaker. They also calculate something which is called, they call it a residence time, but you can think of it, it's a type of, there's lots of different residence times. But this is one way of measuring or estimating residence time. And so they said, well, how does this, having a barrier there, affect the residence time of the system? And so this is showing the base case where you have residence times for the time since the particle exchanges with the coastal ocean of sort of months to almost a year. And they show, well, how has that changed? And so in general, they show the residence time increases once you have less tidal mixing. But again, there's some structure to that. But that's sort of, for the Chesapeake Bay case, that's particularly important because they have such big hypoxia issues. And so if you increase the residence time, then you potentially increase the risk of hypoxia, which is low oxygen. Again, I want to mention there are some important differences between the Chesapeake and the Hudson. The tides are much weaker there to begin with. And so the effects of the barriers on the tides is less pronounced. It's also a much deeper system, and as a result, it turns out the tide's not the main way itself mixes in the Chesapeake. The Chesapeake is very much a wind-driven system, in addition to the tides, but the wind is important in the system. So again, that's sort of an important difference as far as modulating the changes in the Chesapeake different than the Hudson. Okay, so just to summarize, there's really not a lot of studies out there, which is why we need to fund more of them. But I think this is pretty, the key difference between the barriers that are out there and the barriers that have been studied and the Hudson is that there is this difference in estuarine physics where you have the estuarine circulation and the stratification both depending on tidal amplitude. And I didn't go into detail, but it's not just a linear dependence. It's actually a non-linear dependence. So there's it increases with a power of the tidal amplitude, such that a small reduction in tidal amplitude can greatly increase the estuarine circulation and the stratification, and thus increase the import of salt into the system. And so that's sort of a key difference from in this partially mixed type system compared with more tidally driven systems. And then there's this potential for greater salinity intrusion and stratification, and then also potentially longer residence times, but a lot of spatial structure depends on the details of how you influence barriers and so forth.
A few people have asked to explain what residence time is.
Yeah, so residence time, you can think about it, is how, well, so this it's a very rich topic in the sense of residence time of what? That's really the important question. Residence time of a parcel of freshwater that comes from the upstream end, residence time of a parcel of freshwater coming from the downstream end, residence time of some, I don't know, piece of sediment or some piece of biology. And so you can track the residence time of anything. And so once you've decided what you're tracking, then it's how long that thing stays in the box that you care about. So you can think about how long it takes a parcel of fresh water that comes from the watershed to move through the estuary and get to the ocean, on average. And again, this is an average quantity. It's a very rich topic. Okay, so I think with that, I'll go ahead and pass it off to Philip to start talking about some of the model results. If, unless, yeah, that's probably a good idea. Yeah.
We're going to load a new PowerPoint, so we'll be a minute.
One useful thing to know about residence time in estuarine systems with a lot of agricultural runoff, most of them estuaries with a lot of agricultural urban runoff from wastewater treatment have too many nutrients. They're eutrophic is the term for it. Too many nutrients, and that can lead to low oxygen levels. So if you increase your residence time, those nutrients and those nutrients are trapped for longer, and you tend to have more problems with oxygen. So that's why we care about residence time. That's one of the reasons we care about residence time. All right, so Philip Orton, Stevens Institute of Technology, and I'll be speaking on the modeling that Dave and I did with these pre-existing models, looking at the physical influences of surge barriers in the Hudson River estuary. All right, this is an animation. If you can't see it online, you should be able to see it, but if not, I'm still going to make my main points. It's an animation of Hurricane Irene in 2011. This is water elevation with the shading. It's, the arrows here are 25 meter per second, 50 knot wind. That's the scale. And you see the storm coming up the coast, and you see the high water levels reaching New York Harbor. So hydrodynamic modeling, which we've shown a little bit of the results so far, it's computational modeling with mathematics that accounts for the forces acting on water and the responding motion of the water. And so the water flows. So that's what you're seeing here is there's the force of the wind dragging on the sea surface, causing storm surge. You're also seeing the force of tide that we impose on the boundary from a larger scale model, ocean model, and those pressure forces of water that's deeper in one place, higher in one place than the other, the gravitational force is a pressure force. So you see these different forces acting on the water. You also see the fresh water coming down the Hudson when the animation ends. You'll see the Hudson light up in red at the very top. That's the freshwater volume being added to the model in the very northern part of the Hudson. So you can see it glow red at the very top. So there's these different forces acting on the water. That's what a hydrodynamic model does. It's got about 500 cells by 200 cells. So the world's divided up into these different boxes. It's got 10 layers in the vertical. So over these order of 100,000 cells, you're computing the momentum and you're budgeting basically beam counting. The computer is doing this for all these computations every second for the length of the simulation, in this case about 8 days. And so we also can look at a section in the vertical up the Hudson. So this is a case looking up the Hudson from Battery on the left to Albany on the right. The bottom is salinity, shaded salinity. The top is shaded water speed and arrows that show the water velocity. So it's not animating yet. I'm just going to explain it first. The black area is the bathymetry. It's very distorted. If you think about it, this is 200,000 meters across the x-axis, but it's only 20 meters on the y-axis. So it's just really distorting the vertical in a funny way, so it looks very jagged, but the real bathymetry has really weak, much smaller slopes. So you can see the salt content coming in, the salinity of the ocean water coming in on the left, and I'll animate it now. This is Irene again. So I always really like this animation for capturing the different things that are at play. So we also have conservation of salt and heat in these models. So we're beam counting the salt and the heat also. We need a lot of accountants if we didn't have computers, but we don't, thankfully. And so you can see how the salt's trying to penetrate up to the mountains, the Hudson Highlands. Poughkeepsie is right here, so it's not penetrating that far during Irene. And after the storm, it really gets washed out to sea. You can also see the tide coming into the system, and it's a wave. The tide's a wave. When you look over 1,000 kilometers or 250 kilometers, you can kind of see the wave-like behavior of the tide washing into the system. And then at the end of the animation, you can also see, and these lines are just flood levels from natural weather service. At the end of the animation, you can see that you'll get a river flood when the rainfall occurred in upstate New York. You get that extra water added in here, and you'll see the water level rising right here. So that's after Irene passed. The seawater gets pushed out by all the river flow, very strong river flow and a high river flood that's kind of held in place by all the friction of sediments and gravel in the neighborhood. So that's how a hydrodynamic model works. That's what I'll be presenting some of the results from this model called NIHOPS that's used for our forecasting at Stevens. So why do we say this is preliminary in this study? The modeling is preliminary. We have these models already that study, allow us to study surge barrier estuary influences with some detail. With three-dimensional modeling, we can capture estuary stratification, the layering of saltier water at the bottom and pressure water at the surface, and the circulation. And we also have fairly complete, characterization of the system's complex attributes, such as all the river inputs and tributary inputs in some of these models.
They lost the audio.
Let's look into that. So why don't I back up one while we're fixing it?
Oh, now it's back. Okay.
Is the audio back?
Yeah.
Great. All right, so we also have fairly complete physical characterization of at least many of the major factors influencing the water, like the wind, the freshwater inputs, et cetera, even down to the level of, in the NIHOPS model, we have wastewater treatment inputs, which in the summertime actually sometimes are larger. That amount of water coming from wastewater treatment around the urban area of the system is greater than the tributary inputs into the river, the natural river inputs. So we capture that. So we have a lot of information, but then we don't really have the resolution we would want way out at the harbor entrance at Sandy Hook to Rockaway. We didn't plan, as Dave said, we didn't design these models to resolve gates out there. So if you want to resolve those narrow gates, the big navigation gate might, in the case of Boston's barrier, is 1 kilometer wide. We can resolve that with say 10 or 20 cells across the gate. So that's a 50 or 100 meter resolution that we would need. And then if you have flow gates that are off to the side, there can often be these flow gates that are just for allowing more flow and not for navigation. And if those tend to be smaller, if they're 50 meters wide, you might need order of 5 meter model resolution. We definitely don't have this with these models. So to accomplish all this in one model would require additional funding, or additional collaboration, bringing us all together. So quick analysis. So we're doing a quick analysis here using the existing available models and grids, CCOM 3D, ROMS, and ADSER. So you may have heard of these acronyms before. CCOM is a 3-dimensional model. We're using the NIHOPS domain, New York Harbor Observing and Prediction System. It's been used a lot for rapid modeling at moderate resolution, I would call it, order of 100 meter in the harbor. And it's used for risk assessment, where we simulate 1,000 different storms that could occur. It's used for probabilistic forecasting, where we'll run 100 weather forecasts from the European model, the American model. So it's a good fast model. It can be run quickly with a lot of different, accounting for uncertainty in those cases from different weather forecasts. The ROMS modeling system with David Ralston's own grid we also ran, and that's been used for a lot of very detailed studies of estuary physics and circulation. It has higher resolution than NIHOPS by a factor of 1.5 or 2, and it's got resolution in the horizontal about up to 100 meters, but more broadly through the harbor, it's got a higher resolution. And then the ADSER model is what's been used for FEMA's work, for FEMA's flood mapping on the FEMA Region 2 grid, which is up to 70 meter resolution. That was designed for flood and tide modeling. It's not a 3-dimensional model. It doesn't capture the vertical layering and it doesn't include salinity or freshwater inputs from the rivers. But we brought that in for a comparison. What we're doing with each model is we're simulating normal tidal conditions. We're not simulating weather, and we're using average river stream flows into those 3-dimensional models, but not into ADSER. Right, so our approach for this preliminary study of what could happen if you have surge barriers with various amounts of gates at the entrance is to look just at the Sandy Hook Rockaway transect. And we compute this parameter called gated flow area. So it's the relative percentage of openness to flow relative to the natural system. So that's the cross-sectional area, so the depth times the width, with open gates of the system with its gates open, divided by the system in its natural state without any surge barrier and no gates. And then you could also think of that separately. It's like the cross-sectional area of the experiment that I'm running, where I'm putting in blockages to flow, divided by the control experiment, where it's the natural system. All right, so first the CCOM 3D, the NIHOPS modeling results, or setup and then results. This is the whole domain, model domain, which I showed in that animation. This is a close-up that shows we typically have about 10 grid cells across the harbor. It's used for NIHOPS, as I mentioned, for the Stevens Flood Advisory System, and its resolution is 150 by 450 by 10 in the vertical, and it includes hundreds of freshwater inputs and heat inputs into the system. So a very detailed model that's used for real-time forecasting. Here's the problem with the barriers. You can see here, there's only about 15 cells across this region here, and they're much coarser. They're not as high resolution, several hundred meters in resolution here. So it doesn't have a lot of resolution to capture gates at the entranceway. So now I'll show you, so there's about 80,000 square meter cross-section area. That's about 10-foot average depth, 10-meter average depth times 8 kilometers across this span. So when we add in these barriers, what I'm doing is I add in these blockages as just high cells of bathymetry that are above the sea level by 10 meters. So I'm adding it in. This is a gated flow area, GFA, of 80%. So it's still got 80% of the flow pathway in terms of cross-sectional area. And then another case is 62% gated flow area, so it's a little bit less open. And so you're seeing as we close it off, we have fewer cells actually resolving that flow. And then that's the case with just one pathway for the water at 15% gated flow area. So we do that with all three of the models. and I'll show details on the other models. So the negative is using CCOM on the NIHOP grid here, it's very coarse resolution at those barriers. So in some cases, it's only 1, 2, or 3 cells at most, really, that the water can flow through. And that could lead to a bias in the results, so we're aware of that. So we want to think of these results more between the models and think about it more qualitatively, perhaps, when we really start to choke off the flow. But the positives are it's a model-based forecasting system with extensive detailed information on the system that's baked into it. As I mentioned, the tributary flows, the wastewater treatment flows, and it's a very well-validated model against observations over when it's running real time over several years, including salinity, temperature, water level during extreme events such as Irene and Sandy. So here's some results. So what you're seeing here is the gated flow area 100%, which is control in blue. This is a tide time series over 2 weeks of time, or one week of time from a neap tide to a spring tide. So the neap tide, you see smaller tides, less tidal energy in the system. Spring tide, stronger tides. It's all from a location on the left that's from Upper Manhattan. So you're seeing the control case, 100% gated flow area, and then 62% and 34%. And you can kind of see that there's a little bit of a muting for the from the control case in the low tide or the high tide, and then the 62% and then the 34% really starts to reduce the tide more substantially. But even with the 62% gated flow area, you do see some reduction in the tide range. The low and high tide get muted out. So a computation of tide range conveyance for gated flow area is 62%. It's 1.28 divided by 1.35 is 95% conveyance of that tide range into the system. So that's one measure we came up with for estimating the influence on tides. And so now on stratification, or the vertical profile and cross-section across that same location of northern Manhattan of salinity, you're seeing that there's typically, in a spring tide, it's fairly well mixed. And you're just seeing maybe 1 or 2 parts per thousand, or PSU, of vertical salinity gradient. But then if we go to and that's the control, we go to a 62% gated flow area, you see it increases the layering a little bit, the difference from top to bottom of salinity, which we're calling stratification. And then if you choke it off to where you have 34% only, so only a third as much cross-section area, it's much more clear of a difference. And it comes during a spring tide, it's becoming stratified. So that's a real big change.
So what happened to 80%?
I'm just showing, trying to keep it short.
Okay.
I'm not showing all the differences. But I will show, okay, so that's a great question. And that at the end, I'm going to show 3 synthesis plots for each one of these variables we're looking at. First, for the tide range change across all models and gated flow areas, then for the stratification change, and then for the salt treatment change. So you get to see a synthesis at the end.
At 80?
Including all of them, yeah. Yep. All right, and so, and punchline there is weaker tidal currents lead to weaker tidal mixing, the vertical mixing, and then stronger stratification if you have, as you close off the system. All right, and then in terms of salt front location, so this is the salt intrusion length up the estuary. You can see West Point at a distance from the battery and Poughkeepsie. Poughkeepsie is a particular concern because of drinking water. And what you see is that on a spring tide, you basically push the, during neap tide, as Dave really nicely explained, you tend to have a migration up estuary of that stratification as the salt water slumps its way up the estuary due to weak mixing. But on spring tide, you tend to have be moving the salt toward the ocean. So this is the head of the salt intrusion is the 0.1 PSU, basically where it's turning to be fresh water. So it's the very furthest point up estuary of salt. And so that distance in the control system really fluctuates a lot from after spring through neap, and then after spring it's coming back down again, down estuary. With a small amount of constriction, it just changes a little bit. But then if you have a gated flow area of 34%, a large constriction, then it really changes your spring tide conditions, and you have much more stratification, and that leads to longer salt intrusion after on spring tides. The lower neap spring, so what you're seeing though in this case with low gated flow area is you really have less neap spring variability in the system. Your spring tides are getting more like neap tides. And so your salt intrusion really doesn't have much variability. It goes further up estuary during spring. And so your neap tide's not changing as much as your spring tide. All right, so now the ROMS modeling, which we did with Dave. We prepared the grids and Dave ran his model. Here's the full scale of the model domain. Does it go a little further offshore? It goes, okay, so that's it. It's 100 by 300 meter grid cells. They're uniform rectangular grid cells. It has the same total stream flows as CCOM, but entering the tidal river at Green Island. So that shouldn't really change our results for the lower estuary. So they're being put in at one location. Here's a picture of a gated flow area of 58%. So basically large gated openings through a large part of, especially the deep water areas, on top of bathymetry. And you can see all these points show the grid cells. Basically, they define where the grid cells are, these 100 by 300 meter grid cells. Here's 43%, so you see a little bit more closed system, 24%, and 12%. So just looking at that case, which we've seen in some pictures before, I don't think it's realistic that the board would propose this, but we've seen it in some pictures, so we made some scenarios of having lower gated flow areas. All right, so the negatives of ROMs in this application are it's better resolution than the NIHOP CCOM application, but quite a bit better at the barrier, but it still has somewhat low resolution. And one issue is that there's a rotation of these cells that's they're not oriented directly in through that opening, which was the case with the NIHOP application. So that may also require, if you have a case where there's these really narrow gates, we're worried that they don't circulate as well as they would have if you had cells oriented through those openings, and the water flowing just from one cell to the next without having to go diagonal. The positives are it's a higher resolution grid, bathymetry, and twice as much vertical layering, 20 cells versus NIHOPS. It's a well-validated model for salinity and stratification, which NIHOPS hasn't been as validated for. So I would trust this model more for its stratification being exactly right, or closer to being right. They're never perfect. They're definitely, a modeler should never say exactly. Talking about someone else's model. And so also over a wide range of questions. And so his results for the tide range, for the tide time series in this case, show that there's very little change for a gated flow area going from 100 to 58, 100% down to 58%, but then when you hit 44%, it starts to go more, but really at 25 and 12, if you have a much lower gated flow area, then you have a big drop off in your tide range. So there's maybe even some point where things change a lot, and understanding that point would be really valuable. But these are more subtle changes for the 58% and the 44% in terms of your tide range or your high tide and low tide. And then looking at bottom salinity, and on the x-axis we've got bay, just focusing on this panel first. There's a few things to introduce. So you've got your up estuary distance on the y-axis, your day of the simulation, of this tide simulation up to day 50 on the x-axis. The black line is the tide water level time series. So you see a neap tide, a spring tide, and a neap tide, and more a weak spring tide. And you're seeing shaded your water level over here on the far right. I mean, not your water level, your PSU salinity from 0 to 30. 30 is red, purple is 0 salinity. You also see a white line, which is the 1 PSU. I use 0.1 for my salt intrusion lens, but he used 1. So that's the salt intrusion, the max, the limit of the salt intrusion of the estuary. And so that white line stays on all the panels, or actually the gray line stays on all the panels, showing what the control case has. So you can see the difference in the salinity intrusion. And you're seeing, what you're generally seeing is that there's not a huge difference for a 58% gated flow area, starting to be moderate in spring tide and after spring tide for a 44% gated flow area, and then really dramatic when you get that point where the tides really change a lot with the lower 25% gated flow area. Then the salt intrusion really becomes kind of more constant, not much spring neap variability. And stratification is a similar picture. I won't dwell on it too long. It's capturing much of the same, and we've got some of the same attributes on here. We don't see huge differences in stratification. If anything, there's a difference in this period after spring tide. There's a little bit difference here with a 44% gated flow area, but then a real dramatic change in the whole system at some point. There's a lower gated flow area in terms of stratification, and that's top to bottom difference in salinity. And we did look a little bit with both models, ROMS and ECOM, we looked at the velocities around the gates to better understand what's happening. Dave made these nice plots that show on the, this is the bathymetry in the middle, but on the left, is the control grid, 100% gated floor area case, and you see the water speed on the far right is the water speed for a 58% gated floor area. So you see it going from around 1 meter per second max typically to where it's increasing to 1, 1.5. And then if we go to a 44% gated flow area, you see that you're getting 2 meter per second currents, about 4.5 mile an hour currents. So strong when it comes to shipping, it could be important, but not as strong as what was found for the Boston barrier study. Okay, and then lastly, some AdCirc modeling. I would have liked to have done more of this. It's on a supercomputer, and so there's only 2 simulations with the AdCirc modeling. And so it's a FEMA Region 2 coastal flood study grid they use for their flood mapping, which I've used in a few publications, research publications. It's an unstructured triangular grid cell mesh you can perhaps see here. And it's for the whole Northwest Atlantic. Here we're zooming in at very coarse out at sea, but very high resolution, including the floodplain when you get into the city. So it's for flood modeling in particular. So as you come into lower Manhattan, and then it's even closer to that. So there's no stream flows in this. It doesn't model the salinity differences. It's just a 2-dimensional model, but it has higher resolution out at the inlet where the gates are. So that was a reason to test it out. And so the 2 cases are gated flow area 60% and 37%. And so now I'm going to show those synthesis plots that show everything on the different models and the wide range of gated flow area on a single plot, which I think is really informative. And so here you've got your gated flow area from 10 to 80%. Like I said, control is 100%, so I'm not showing that here. And you've got your tide range conveyance. So the tide range conveyance is computed as 100 times the ratio of the tide range in the experiment with surge barrier divided by the tide range in the control. So for cases above about 50% gated flow area, you've got something 95% or above tide range conveyance. So very little change in the system. And then when you get to lower, there's some signal that when you get to a lower gated flow area, there might be some rapid decline. Particularly in the ROMS results shown in black, you see a slightly greater decline than the CCOM results. The AdCirc, they agree somewhat well, but they start to diverge a bit when we get to a lower gated flow area, and we didn't try even lower than that. And then another synthesis plot, number 2 out of 3, gated flow area versus salt intrusion length. And this is the change in median salt intrusion. Actually, it's a factorial. It's based on the ratio. It's just the ratio length of the intrusion in the experiment divided by length of the intrusion in the control. So you have a greater salt intrusion times 100. You have a greater salt intrusion in all cases. So with the control, it would be 100. It would just be a factor of 1. But as you go down, and actually the 2 models, 3-dimensional models, agree very well in this measure of salt intrusion. Some discrepancy when you get to really low gated flow area. That could be because of the different. That could easily be because of the different way that we're treating river flows and where they're inputted into the system. But surprisingly good agreement on those. And so you're seeing, just a deviation of just a few percent in the median salt intrusion. I'm not looking at neap tide or spring tide. I'm just looking at the median. When you have a 60% gated flow area, go ahead.
The only thing I'm not understanding is the salt intrusion like going up or down? I should have been that.
It's going further up estuary when you have smaller gated flow area, when you have more obstruction. Yeah. Good question. Okay, and then lastly, the gated flow area versus the top to bottom salt stratification difference. And what you're seeing here also, and so as Dave really nicely explained, there's a high sensitivity of stratification to changes in tides in a partially mixed estuary. And so that can explain why we're seeing these differences. So the red shows CCOM, the black shows ROMS, and we're also showing separating out neap and spring. So in the case of the neaps, they're the circles, and you don't see a lot of change in the stratification in the system. But when you look at spring tides, you're seeing changes on the order of 30%, 25, 30% for CCOM and greater for ROMS. So you're seeing, even at a 50% gated flow area, maybe you do have a bigger influence, on the order of 20 to 50% on stratification. So stratification is very sensitive. Again, this is how it's computed. In this case, it's that ratio, but I'm subtracting out 100, so it's a little bit inconsistent with the last one. It's really a difference this time, so 0 is no change. In the last slide, 100% was no change. So So that's really interesting, and it really shows how partially mixed estuary in general may be more sensitive in its stratification than it is in its tide range to obstruction. So conclusions, and then future, next slide will be recommendations. So both the modeling and the literature provide consistent qualitative conclusions on the physical effects of surge barriers on the Hudson River estuary. More restrictive barriers lead to stronger tidal currents and mixing near the barrier gate openings. But widespread throughout the estuary, there is a reduction in tide range, currents, and vertical mixing. This can lead to increased stratification throughout the estuary due to the reduction in tidally driven mixing. It can lead to a greater salinity intrusion due to the stronger stratification and the stronger gravitational circulation that you see. And more pronounced changes occur during spring tides than on the leap tide. These preliminary results provide a baseline for more in-depth studies, as Dennis mentioned earlier, that can be done now looking at more interdisciplinary topics such as habitat, pollution, et cetera. There's a one-year study that I'm PI on, funded by NOAA NARES, which will hold workshops and try to broaden the scope of this work from physics to other topics. And we'll be doing some more physical modeling also under that project. So that's really exciting. That goes on for just 1 year, starting right about now. And then recommendations for further physics research are that we should continue with three-dimensional estuary modeling of surge barrier induced changes, covering a wider range of conditions, including seasonality of stream flow inputs. We just use the average stream flow input today. Create a new regional or nested model grids that are specifically designed for dealing with surge barriers and their potentially narrow openings. And it would be wise to have resolution sensitivity studies to understand what resolution you need around a barrier gate in order to have results that we would deem accurate, maybe a convergence study using finer and finer resolution models. Continue to develop a more detailed set of estuary parameters like those three that I highlighted in those synthesis plots at the end that describe the influences of barriers on physical or ecological conditions in estuaries, reflecting changes in flushing or residence time, as we were referring to it, sediment transport, inundation frequency as it might affect a marsh, sedimentation on a marsh, and salinity. Also studying closed barriers. Today, we've really focused on the open barrier system and what happens to normal conditions in the estuary, but there's a lot of research that can be done on the risk reduction as well as of barrier systems, as well as the possible problems that could be created from heavy rainfall during a storm, wave reflection, sediment erosion or deposition. And these will be studied, and hopefully the more we can study them, the better. And lastly, study the possible optimization of surge barrier designs, working with engineers and scientists together. We could potentially have synergistic work that tries to look at the balancing of cost, benefits, impact, and navigability, and evaluate storm surge barriers instead of having scientists and engineers work separately on the topic. And that's it. Thank you very much.
Go ahead.
Yes. Hi. First of all,
Can you say who you are?
yes, I'm Richard Webster. I'm the legal director of Riverkeeper. But actually, before I was a lawyer, I used to be a hydrologist and a modeler, so this is kind of fun. Like going back in time. And first, I want to say, you guys have done an amazing job in a very short period of time.
Thank you.
And it's just so impressive, and the seminar is absolutely fantastic. So now my question. Sediment transport modeling, and that's pretty hard in estuaries. This is it's already been a tough job to accurately look at the physics of the water flow. Are you proposing to add sets into this model?
Yeah, so yes, we actually, it is hard. It's definitely very hard to model sediment. We do it. And actually, as far as the way fine sediment moves through the system, moves through the estuary, we've also done a lot of observation. So we kind of have a sense of how well we're doing, what we're doing. And so I think one certainly next step would be to take a similar type of approach and use what we have now as far as the model sediment in the system and look at how that impacts changes. And you think about changes happening both sort of so the main source of sediment is the watershed, comes from the river, moves down through, a lot of it deposits in the system. And so how that transport of sediment from the watershed changes. You also could have changes in circulation patterns, which change the scour and potentially remobilize the sediment in the estuary. That's a separate question. I think both those things would be worth looking at. Yeah.
That's a good point. So do you have funding to do that? And if so, how will it?
So we've done sediment transport with funding from lots of great sources, including the foundation, in the past. We do not have funding to do future work on this yet. So.
Do you think we should have funding?
Yeah.
Not the end.
Okay, we'll do the future.
Go ahead.
Yeah, tough question. I don't even know how to ask it. But
Who are you?
Rick Hirsch, New York City resident. Is there a general number you could give us to see the volume of the water, salt and fresh and location, let's say somewhere around Manhattan? I'm familiar with CFSs, but how much fresh water is coming in versus, I'm just getting a feel for the power.
Yeah, so the volume, the river volume we put in was 500 cubic meters per second. Oh, sorry, let me repeat the question. You basically want to know what the volume of transport was of, I think, tidally, presumably. So I'm going to start with talking about how much is coming from the river. So that's fresh water, so 500 cubic meters per second, multiplied by 30 to get to CFS, roughly, ballpark. So somebody else can do that math while I'm talking. But so the important thing is that corresponds to a mean velocity of something like 5-ish centimeters per second moving through the system. So that river water is moving down through the estuary at about, on average, because it's always coming in our model anyway, moving at 5 centimeters per second. The tides are roughly a meter per second. So there's 20 times as much volume sloshing back and forth every tide as the river's putting in constantly. And obviously, the river discharge is changing through time, but yeah, so it's an important thing to keep in mind that the tidal sloshing back and forth is much bigger than the volume just passing through the system.
Lower.
Well, actually, at any discharge. Yeah, at any discharge.
And you can also look at the salinity and say, well, this water is riverine. You know, if it's got a salinity of 20, if it had a salinity of 17.5, say off at northern Manhattan or Tappan Zee or somewhere, then it's 50% pure ocean water, 50%, you know, over time. So it gives a slightly different perspective. But definitely the energy in the system is really strongly driven by tides. Because it's such an open system to the ocean, I think it's a big factor. It's not a massive river system. Go ahead.
I work out of Hudson, and up there we have increased temperature up to 90 degrees. And I didn't see much in your discussion about temperature changes. But we had so many mussels and barnacles on our boats that we had to have divers go down and scrape them out before we could even leave the piers. And I was just wondering if that had any effect on what you're discussing.
So I was asking, so that was that for the summer? It peaked out at about 90 degrees Fahrenheit?
Last couple months, yeah.
Yeah, so the temperatures in the Hudson up by Haverstraw, north of Tappan Zee, peaked out this summer at a very hot temperature and caused some problems, barnacles, you said, et cetera, some more biofouling. And so how would, we did not look at that in this. I think if you have a longer residence time in warmer seasons, you could have warmer temperatures.
But I think an important thing too is in this system, so temperature affects the density of water, but the effect of salinity of salt is much stronger. And so when we think about physical changes as far as how water is sloshing around, the changes in salinity are much more important than change in temperature. Certainly, if you're an organism growing there, the temperature matters, and that could be affected by the stratification, for example. But you're right, we didn't actually look at that sort of knock-on effect.
Yeah, and that explains why we looked at salinity first, because it impacts the circulation in a much bigger way.
Let's go to the back.
Keep wait for it, I'm wondering how the resolution, if you know, of the Army Corps study of the models they are likely to use correlates to the resolution of the models you use, and sort of what if you can sort of comment generally on that. Is there a lot of recommendations that you made for future research that make a lot of sense to consider as part of that, or maybe a later stage, including the frequency of closure of these things and sort of how that might affect physically and ecologically with this discussion. But I'm curious if you can comment just generally on resolution and how some of the recommendations may or may not be used.
So the question was, do we know what the Corps' modeling resolution is or will be, and can we comment on the importance of resolution for the modeling? and how it may relate to our work. And I would say that we don't know a lot about what the Corps is doing. My sense is they had less money up front, and they're looking to get a lot more funding for doing more research. But I suspect the Corps will use very high resolution in their work, but I don't know for sure. Does that answer? No.
I don't know anything about the Corps.
Yeah.
I'd like to keep it that way too. But back to that.
Katie Friedman, I'm an aquatic ecologist in New York City Park. And my question is about looking at seasonality, trying to help out. Particularly, would you be looking at historic seasonality flow or potentially incorporating differences in precipitation and drought?
And you're not talking about climate change, you're just talking about capturing all the range of variability that can exist.
I'm thinking particularly fixing salt front and the
Yeah.
data that you can use so far is average flow. You know, they get nervous about freshwater, without barriers.
So the question is, are we considering a full range of historical climatic variability or weather variability from drought to more extreme rain conditions? And it's definitely something we'd like to see done and we would recommend to be done. First thing would be to look at typical dry summertime. You know, we didn't look at that, and that can go on for many months at a time. Not this year, obviously, but many summers are very dry. And so that would be a first thing to do, but definitely there could be a fairly comprehensive study of different types of conditions. With the closed gates, it'll be interesting to look more comprehensively at what happens when there's a lot of rain during a hurricane. So far, the results have suggested that when there's a lot of rain during a hurricane, it's a very large watershed, and there's a timing delay from the storm surge to the rain flood, but 1 day or 2 days, and so that's still something that should be studied a lot more comprehensively to better understand if that could be problematic, that you close the gates and you have water rising behind the gates. Go ahead.
So, two quick questions. One, Mark Johnson, landscape architect and ecological restorationist, New York City Parks and the River Project. So I wonder, on that 1974 situation where the river in Maine removed an obstruction, if you came across what their motivation was, why did that close that causeway? Why did they open it up again?
I don't know. Probably lobsters. I don't know. I really don't know. I have no idea actually. Yeah.
Okay. All right. And the second one is whether any of the studies that you looked at from other places, by contrast with gates that would go from essentially the top of the water to the sea bottom, were any of those other examples or other ones that you know of, ones which had an opening at the bottom or were more floating or, that didn't close the entire water, didn't go down vertically through the whole entire column?
Like I said, there really haven't been that many studies on any types of gates, with the exception of the Dutch ones, and I think those are not that yet. They're fully blocking the water. I don't know the details of the gate design. We tried to stay away from that, at least initially. Although it is a really important point, because once you start increasing your resolution, you start resolving a lot of the flow structure, and that becomes then dependent on how exactly you implement your gates.
So just from a physical perspective of water hydrodynamics, can you make any kind of comment about what would be an option to consider that would be effective for controlling storm surge, but would allow a lot more flow?
Well, having more gates is the solution if somebody's choosing storm surge barriers. We could talk forever about other crazy ideas that I might have to solve flooding problems. But if you're having a surge barrier and you have more gates, then and you have a gated flow area that's 99%, 100%, you could, this is impossible. But if you could have these opening gates and the navigational gate that's larger, then it costs a lot more money, but then you can have you could feasibly have a negligible impact in the estuary. So that's the solution that this could steer, this type of research could steer the Corps in a positive way toward understanding better what would have a negligible impact. Go ahead.
So, Savannah Geronimo, I'm an architect and volunteer member of the Storm Surge Working Group. I was wondering if you could supplement your research to go into the that 80% kind of column, because you kind of started out at 62, 58, you went down to 25, and so you kind of ignored everything kind of above 60. So I mean, maybe something around a 75, 80%, if you could just pull that out and supplement and maybe do conclusions and stuff. Is that possible?
So the question is, we focused more, we had more data points on gated flow area below 80%, maybe even 50% and below than we had for the high values with minimal obstruction. Can we focus, and will we focus more on the area of that space above 80% where there's very minimal obstruction? And I think that's above 60, yeah. So of course, you know, we started this by looking at what we saw online on the internet and saw something that reflected 10 or 20%. So we made that model, and then we moved in the direction you're speaking of as we went on. So absolutely, I mean, and as the model results and the models get better and the model results get more comprehensive, I think it'll steer toward what's of interest to the Corps. I know in my one-year project, we're working, you know, trying to work and help the Corps and interact with the Corps along the way to find out what they want to see more of that would complement their research.
I hear you, but my question is, can you supplement this report and show that something over 62% and an 80%, 75%? Because
Well,
you just pulled the numbers
yeah,
out, right?
yeah, I can, because I have this one-year project, so that's a good idea. So yeah, it won't be part of this report, it'll be additional work, yeah, but it's a good idea. Go ahead.
Okay, an online question. Noah Chesman asked, Noah Chesman is from the Wildlife Conservation Society's New York Aquarium. Does your analysis and the model take sea level rise projections into account? If so, what sea level rise projections are used?
No, we're looking at much shorter time scales. Yeah, so the question was about whether our models include sea level rise, and so we're talking about much shorter time scales. Again, we're looking at sort of the month time scale initially, so the change in tide of a month, which that'd be a wholly separate issue.
I think that's another nice thing that could be added to our impacts, you know, to our list of future work, because this would be there for 50 or 100 years or more. So one would want to think about what the impact might be with deeper water with higher sea levels. So that's definitely a good, one more thing for the list. Who's keeping the list? In back.
I'm Ralston, I'm writing a dissertation about the airport. But I'm wondering, in your model, if you can see what would happen to the waterfronts of the Rockaways and Sandy Hook with the introduction of these barriers, because I'm assuming that with the increase of velocity, pushing the gates, and with storm surges, that you have really different tidal flows hitting those areas. So I'm wondering, what you would show.
Yeah, so I think that's certainly, I mean, as I sort of hinted, so repeating the question, I think we're basically looking at how the barriers might influence water levels and currents at other parts of the shoreline of New York Harbor and even outside of the harbor, I think. Is that what you said?
The Rockaways.
Okay, so on the outside of the barriers, which is, it's a very good question. And that would be something which I think you'd want to look closely at. Again, I think, like for example, speaking from my modeling, we've mostly focused on what's happening inside the estuary. So if I were to try to address that question, I'd want to set the model up a little bit differently, such that, essentially we're better representing those processes there. We have them there now. I just don't trust them fully. But it's a very important question. I think that would be something you do. And I sort of hinted at by that study from Chesapeake, where you can say with a change in tide, on average something like a 20% change in tide, but there's a lot of spatial variability. And in fact, the Chesapeake showed that the tide was amplified on outside the barriers, which again makes sense from a reflection point of view. And so that certainly would be interesting.
And another thought on that is, if you reduce the tides in the system, Dave can answer this better than I can, but it's a thought. Do you reduce the flushing of sediment to the coastal ocean if you're reducing the tide in the tidal river and in the estuary? And that could be a concern that you might have less sediment delivery. But he might even be able to.
Yeah, that's very, I don't know what the answer is, but that'd be something you'd want to try to address. And you're thinking about, for example, connectivity between sediment coming down the watershed and going into Jamaica Bay would be an interesting question.
And is the erosion problem of the Rockaways already a huge issue that the Army is always putting in dredge material to shore up that beach? And I imagine that with the introduction of these caves, that would be becoming
Well,
sense of that?
yeah, and so that's sort of a detail there, that a lot of that is wave-driven processes, so you want to incorporate that as well. And so basically address how wave-driven processes are altered by these 6 barriers. So it's not just the tides, is what I'm saying.
Malcolm? Malcolm Bowman.
Malcolm Bowman, physical oceanographer at Stony Brook University and chair of the Metro New York, New Jersey Storm Surge Working Group. Firstly, thank you for this great presentation. I think it's the beginning of a long process, evaluation of what's obviously a very complicated issue. I mean, the big question really is, can human civilization, as we know it, coexist with a Hudson River that remains in a healthy ecological state? I would say, cautious, yes. Just a couple of comments. You mentioned first about tidal mixing, and this needs to be studied a lot more. So obviously, some engineering structures can mix up the water column. And to my mind, that may actually be a positive aspect of this, because if you look out the window here and see this beautiful harbor, crudely speaking, the harbor and the tidal flushing and circulation mixing is really an extension of the New York City sewage treatment system. Oh, it really is. And as you said, Philip, during summer conditions of low Hudson flow, that there's more water coming into the harbor from sewer outfalls than the tributaries of the Hudson River. So it's a big issue. And treatment of sewage relies a lot on aeration of water columns, bringing oxygen to the atmosphere and mixing with water. So there may be a benefit. I don't know, but there may be a benefit of enhanced mixing. And the other final point, you mentioned in passing the need for a second barrier of Upper East River. And some might say, well, why do you need a second barrier? Doesn't the big barrier by the south of the Ralston Bridge, isn't that all we need? Well, the answer is no. If you look at Sandy, there was actually 2 storm surges. One came up from the ocean through the Ralston, and it was tied to about 9.5 feet above normal, and occurred at high tide during the spring tide, right? But there was a second surge that come roaring down Long Island Sound, driven by that noisy wind. That surge was actually higher than the battery surge, which was like 14 feet, but occurred as the tide was dropping into sound. So that's a very important aspect. The whole study I think, in the future, it's not just this barrier, but the 2 working together. And also, maybe this could be a discussion topic in the future, that if that Upper East River barrier were operated in an imaginative way of what we might call a check valve, or bringing clean Long Island Sound water up through the East River, that would have a very positive effect on water quality during good weather. So, and so reducing those excess nutrients in the harbor is an important conservation issue. So it's very complicated. So I just encourage you to broaden your thinking about the whole system, not just this big barrier.
Thank you, Malcolm. Yeah, Malcolm's at Stony Brook, and his last point is one that's been brought up and proposed before, is that you could use a Throgs Neck barrier up on East River, which is part of this system we're talking about. That belongs there to stop storm surge from coming from Long Island Sound. We didn't talk about it much today, but that's there also. And there's been some proposals to use that in coordinated ways to improve water quality. And so water quality definitely is another order of magnitude, perhaps more complicated study that would be useful.
But I will say, I mean, I totally agree that there's the increased tidal velocities, the barriers are going to increase the tidal mixing, and I think that's shown in reductions in stratification. And the stratification essentially is the same issue of the water quality and excess nutrients. The issue is, because there's all that strong tidal flow, there's a lot of frictional loss there, such that inside, much of the rest of the estuary, the tides are smaller. So the tidal velocities are weaker throughout the rest. And so it's that trade-off, right, as far as you get enhanced mixing in a small region near the barrier, near the mouth, and then you have reduced mixing in the rest of the estuary. So that's what you want to try to address.
Go ahead.
Let everyone ask one question first. Is that all right? Can we have everyone ask one question first?
That's a good idea. Anybody else?
Matt Shelvis, New York State DEC's coastal program, also the state's project manager for the HAS project. I was curious if, as part of the NOAA project, you guys were planning to look at any other barriers that were proposed into the Army Corps alternatives, like the Frog's Neck barrier and several of the other ones. So we have, for you guys, we're gonna focus, strictly on the large barrier that goes from Freeport to Sandy Hook.
That's a great question. The project's funded by, the NARES system, and the Hudson River NARES is the most interested end user, or one of the interested end users and part of the team. So we may focus more on the Hudson, but it's a very good point. We could, we certainly can do some of the same work and look more closely at the Frog's Neck barrier, for example, and I don't think we'll look at Jamaica Bay barrier, but that's another one. We could look more broadly since there's such a broad interest from the region, so open question. And he had asked if we were going to look at other barriers other than this one and its influences on the Hudson. Go ahead.
John, we go 6 findings. You keep coming up with ways to expand the study. But one thing that I'm wondering is we're sort of taking existing condition as what's out there now. But I wonder historically, if you looked at what the flows were like and mixing was like before man got here and started dredging the channels. It was probably much lower flow, maybe closer to what it would be like once the barrier goes in originally.
The question was if we looked at historical conditions in the Hudson and thought about the historical change that has occurred, which may be quite dramatic. And Dave?
Yeah, so actually I just wrote a paper on that. And so, yes, what we did is we looked at, we took the oldest available bathymetric charts and digitized those and ran a similar type of model. And it turns out there's not that much difference in the tides down here, down in the New York Harbor area. There's a big difference in the tides when you get to Albany, but there's not much change down in the harbor. And so as far as the tidal flushing is pretty similar. There are some changes in the swimming intrusion. That comes back to this basically the fact that the deeper you make it, the more you can extra circulation can get going. And so you do see changes in the salinity intrusion and the stratification associated with essentially creation of a dredge chain. And so I don't know if that's relevant to this particular question, but it's a really interesting topic. So.
Any new questioners?
Well, I think we're online. Online.
Oh, it's online.
Right. Yes. I'm only the online question.
Yeah.
So, Nava Tava from King Hudson asks, what is the range of gated flow areas in the various potential designs for the outer bay barrier, and can that be estimated?
The question was, what is the range of gated flow area on the Corps plan or the proposed outer barrier? And I don't think that's known yet. I certainly don't know the answer to that question.
Yeah, they haven't gotten that far.
They haven't got that far yet in the study yet.
But I think it's got to be realistic, it's got to be very large, like, if we were thinking of a huge solid barrier, 4 miles, say, 4.5 miles, mile of gate, that's not ever going to work. You don't have to be a rocket scientist to understand that. So, when I talk about British, never go below what you call 85% two bands. In other words, a superstructure in good weather cannot reduce it by more than 15%. Otherwise, you're going to get in trouble ecologically. So, the idea of just like you showed for Boston, their plan was all equal dying. There was a huge barrier with these gigantic, what we said, biggest little gates. That's never going to work.
That was driven by, I'm pretty sure it was driven by navigational. The size of the gates, at least in the study that I read, was driven by navigational issues. Basically, having big enough gates to let big ships through. So, yeah.
Yeah, maybe for Dennis, to put this in perspective, does anyone seem to know the total cost estimate for the destruction of Sandy?
I don't know the
The total cost estimate of what?
Sandy's destruction.
Destruction, well, for New York City, I believe it is $19 or $20 billion.
19 or 20 billion.
Yeah.
Good.
And then, yeah, how much for the whole harbor? $79 billion for the region.
Also forget, a lot of people don't get reimbursed if they're small business owners, businesses shut down for weeks. People lose their entire life savings, people lose their homes, and major disruption.
That total just seems so significant, and whatever the cost may be, and that's for one event. I have no idea. Notice I'm not asking cost estimates here. Thanks.
We'll take Richard's question and one more online.
So I've one comment on Malcolm's comment, which was one way to improve the the nutrient issues in the harbors to improve the sewage treatment system that the York City uses to find a slightly more direct approach to building massive area in the harbor. Which, by the way, we are trying to induce the city to do, so we appreciate your help with that. And we'd appreciate Ralston's help with that. The second question is, have you had any thoughts about how the nutrient changes could they trigger big algal blooms, sort of Mexican, Gulf of Mexico style algal blooms?
So the question is, have we thought more about nutrient changes that could be a result of obstruction of the system? And I mean, I would say, when you have a eutrophic system which has too many nutrients, the Hudson for many decades now hasn't had, I would say, a hypoxia problem. It used to have a severe problem before sewage treatment. And you can look at a graph of the past century of oxygen levels in the Hudson, which is really amazing to have. But it's a system that has too many nutrients presently still. And so if you increase trapping or stratification, or increase residence time, then you could lead to that outcome. But again, it all comes back to the amount of openness to flow of the system.
But it's also a couple of problems. The Hudson's particularly turbid system is not much light penetration, and so that often is a gross limiting factor for why you don't get the
So that's on your list of things to get funding for. By the way, have you thought about using remote sensing for corridors with baseline and verification?
People do, yeah. People do it from satellites. There's a resolution issue.
Yeah, right, which wouldn't be tight enough resolution for
We're going online for a question?
One more. This is from Mark Jaworski. Did your study evaluate potential estuary changes to the two rivers estuary associated with the Shrewsbury and Navesink rivers? And if not, will it be included should the funding become available?
Certainly the Corps of Engineers study. When you look at this outer harbor gateway system from Sandy Hook to Rockaway, one of the areas that would be benefited from risk reduction for flooding would be Shrewsbury and Navesink. In addition to all the New Jersey, areas down off Raritan Bay, but Shrewsbury and Navesink are the two estuaries nobody's probably heard of that are in the northern part of the Jersey Shore back there. So they would have protection. Great question. I don't know. We're definitely focused on the Hudson here, so we haven't looked at changes to any other of the estuaries, the Hackensack, the Passaic, the Raritan, the Shrewsbury, the Navesink, et cetera. But these all could be studied in the long run. Yeah, and that's an interesting question because those estuaries require the water to come in and then do a 180-degree turn and go back out behind Sandy Hook. So it's an interesting question.
We'll do one more, okay.
It's also a series, sorry. I'm Jessica Rock, I'm the Director of Advocacy and Engagement at Riverkeeper, but I have questions from John Lipscomb, our captain, who's on the boat right now. His question, there's a bunch, so I'm just reading them through. Is it realistic to look at GFA over 25% or so? Are there any precedents worldwide? 25% of Sandy Hook would be 1.5 miles of movable gauge, which would be fragile, complex, and high maintenance. The Ambrose Ship Channel is 2,000 feet wide, or about 7.5% of the length of Sandy Hook Barrier. Are there any examples of ship gates that wide in barriers which face open ocean conditions, not in Rotterdam, where the gates are deployed from shore-based foundations? And finally, we read that the eastern shelf reduced tidal range 30% inshore of the barrier, with 29% GFA. These are off Socrates right now. It's lack of wind flood. How would reducing the tidal range 30% in the upper estuary affect the ecology of the estuary above the salt fresh mixing zone?
That's all.
Yeah.
Yes, there were a lot of questions there. We're not going to repeat them. I think the gist of it was, is there sort of precedent for, or what are some comparable gated flow areas in other parts of the world? And so the numbers that I saw were definitely sort of in the lower range. Again, not every reports it the same way, and so I'm making some guesses, but it's in this sort of, certainly less than 40%, and down to 20% for some of them. And then as far as engineering a big gate, I'm not that kind of engineer, so.
Can I make a comment on that?
Yeah.
I think people are picturing the barrier, or whatever it is miles and miles and miles with an opening. You try to make that as big as you can. Real barriers have sluice gates in them, which are a series of gates that are not for navigation. They're for the purpose of keeping the barrier as porous as possible. So a barrier would likely have that. Now, your paper talks about how the flow through smaller openings is different through light, and that's important.
Yep.
But it's not just how big you can make the gate, And as far as the Netherlands being land-based operation for the gates, so would these gates be in the versions that have been shown of the outer harbor barrier, because you build land, and that's where the gates live.
Yeah, that's an excellent point. And so I think that comes back to our recommendation at the end, that I think going forward, it'd be really great to have engineers and or scientists collaborating on these topics, basically to make sure it's a realistic representation of the gate and vice versa. Realistic representation of the natural flows. And then the last thing about the changes on the ecology, I think the first thing that comes to mind is if you have a reduction in tidal amplitude, then obviously it changes the inundation, and so potentially changes, marsh conditions in marshes. But
one quick thing, you asked how much money was lost during Superstorm Sandy. Roughly 44 people died, and from right near here, we have a person drowned. We have the New York Stock Exchange on Bond Street. Another person drowned in Tribeca, and I don't know how you're going to put a price tag on people drowning. I just want to remind people.
Good point.
Yeah, I'm not trying to answer that point. I mean, I think one thing that I just mentioned is that, what we're trying to do here at the foundation is not make a determination as to what's the best way to prevent, to mitigate the hazard, whether it's from storm surge barrier, whether it's from storm surges or coastal storms or spills, which is, results in persistent flooding and even more kind of potentially tragic circumstances. So, I think, it's important to keep in mind that for Dave and Phil's work, our focus is really on looking at those ecological impacts, the hydrodynamic effects of one potential solution. I think the answer to whether, I don't think anyone's disputing, and certainly, position here with the harbor estuary person is that, both storm surges, coastal storms, the risk of sea level rise are important challenges that we need to come to grips with, and thinking about things at the order of magnitude of a storm surge barrier across the mouth of the harbor is the right scale that we need to be thinking about. Whether or not, I think, again, we're focused on one aspect of that question, and there's many other questions that would need to be addressed, whether or not, this is the right solution for mitigating.
Thanks for bringing that back, Rob. But that's a perfect, I think, ending. It's an ending for today, but obviously a start, as we can all see. So thank you to our speakers. I have three very important announcements. The first one is we have a meeting in this room this afternoon, and as soon as I'm done speaking, our staff is going to be putting this room back together. So we'd love to have you folks here, but we're going to ask you to try and migrate in this direction so we can get our work done. Second of all is that this webinar is being recorded. So if any of you would like to see it again, it'll be up on the website later this afternoon. Yes, with the PowerPoint. And our next seminar is going to be December 4th, and Frank Nietzsche from Columbia, from Vermont, he's still here. He's going to be talking about sediment transport in the Hudson River with his colleague Tim Penna. Encourage you all to come. And again, thank you all for joining us. Thanks very much.
Thank you.